Okay, cool. Well, firstly, hello to everyone here, and let's get started. So, uh, welcome to the first Retro Week Lightning Talk. This is called Plancal Cool. So, this is about the first ever programming language. So, first, I'm going to introduce you to a Mr. Konrad Zuse. Okay, so Konrad Zuse was born in Berlin on the 22nd of June, 1910. So, this is quite a while ago, probably a little bit earlier than we might have thought when we think of like the first ever programming languages, seeing as like computers weren't exactly around back then. So Konrad Zuse was a German civil engineer and a computer scientist, kind of a pioneer as well, and also an inventor, as we're going to find out and see, because he really dabbled in quite a few different things and very much invented some very interesting things relating to computing and technology, especially for way back then. So Conrad, worked as a civil engineer, as an engineer in an aircraft factory, and during his time there, he ended up having to do, a lot of different routine calculations by hand. Things that he would have to repeat on a day-to-day basis, which really, if you were to think about it in today's terms, would be tasks that would just be automated away by some sort of piece of technology or a computer. So this got him thinking, as you do, about okay, back then okay, maybe there's a way that we can kind of begin to automate this. There's surely a way where I don't have to do this job over and over and over again. At this point, we're kind of in the late 1930s, pushing 1940s, so a very interesting time in the world. Remind you, he's also German, so this might this is somewhat relevant. But so this is kind of the beginning of this kind of journey. So Konrad Zuse, as a result of his interest here and wanting to move forward and kind of get a little bit more efficient with his work, he just went and built the first ever programmable computer in 1941. So very much way back in the day, and given the date, right slap bang in the middle of World War II. And also a very, very interesting fact, I think, because Konrad Zuse, overall, very interesting guy, and someone who I think probably most people will never have heard about. So back then, this first computer, the Z1, contained 30,000 metal parts, so a very complex piece of structure. And unfortunately, though, its original blueprints were destroyed by a British air raid, so we're not really able to recreate it back then. But it didn't really work as efficiently as he would have wanted you to, like the mechanical inaccuracy. Like we don't have as accurate machine. We didn't have as accurate machines for building mechanical components back then as we do now today. So Zeus completed his work entirely independently as well of other leading computer scientists and mathematicians of his day. So he built this whole programmable computer basically in isolation. He didn't rely on existing scientific theory and research. He very much just rediscovered parts of computing and a lot of very interesting things about kind of the different types of logic and whatnot. So now moving forward a little bit into then, so we have our first computer and a very interesting guy all around. And now we need to look at, okay, well, the first ever programming language is, what is this? So in building his computer, it's a programmable system. So to begin with, he was working entirely through machine code. And what he found was that this was far too complicated and far too difficult. So he went to do his PhD thesis. And during that time, then, it was around the same time where I realized, look, this is just getting far too tricky and complex for me. So therefore, I need to look into a different way of doing this. So as a result, in comes the first ever high-level programming language, which he designed. So this is Plankalkül. So this is a German word. This is the first name of the first ever programming language, high-level programming language. It was designed during 1942 and 1945. Again, a very interesting period in time. So, and for Zeus, the way in which he kind of thought about a lot of the different uses of it and kind of the way he wanted to demonstrate it was using basically building a chess engine, which is rather impressive for back in the day, especially as a first example program. So here's an example of some Plankalkül code. So it looks like absolute gibberish, but as we're going to see, it actually does follow some of the kind of some of the things we see today. It is a reflection of what some languages are like today in its kind of core foundations and the way in which it's built. So what is Plankalkül? Well, just to break it down, for us now, what we would consider it to be is a typed, high-level and imperative programming language. So there's a few key features of Plankalkül which kind of makes it what it is. firstly, the programs are reusable functions, and the functions are not recursive. Additionally, variables are local to functions to their own programs. And there's only a few fundamental data types. So there's arrays and tuples of arrays, but there's also floating points, fixed point, complex number of records, hierarchical data structures, and listed pairs. So it's a very logical and mathematical based kind of language, but super, super interesting, especially when we see in a minute kind of, again, how it reflects on the kind of like later down the line implementations of languages. So another thing for this type of language, and this is where you might try to kind of, if you've done the assembly module in DCU, you might think of like these kind of ideas. So there's no go-to structure. It's a very logical language. This is an example of an assignment operation. Then we have our so V1 plus V2 can be mapped to OR1. There's a lot of really weird syntax and logic in here, which frankly I don't understand all of. It's really interesting if you want to look into it yourself, but I'm by no means any expert. I think Konrad Zuse is just a really interesting guy after kind of reading into this. So then we have an example of a conditional statement. So V1 is equal to V2, so then mapped to OR1. So this means we compare the variables V1 and V2, and if they are identical, then assign the value true to OR1. Otherwise, assign the value false. And that true false thing kind of brings us into the whole idea of kind of the primitive data types that exist in Planck-Kalkül, which I'll get onto in a second. But overall, it's really interesting because even though it was such a primitive language and like really early on, there are still possibilities within its design for defining subprograms and loops, which is pretty, like when you think of it back then, it's a pretty interesting advanced thing, especially when you realize that he did all this by himself in isolation. So it's also built then on logical operations through predicate logic and Boolean algebra. So a lot of that really boring comparative programming language stuff and logic module and whatnot. So it's built on a single primitive type, just at one bit or a Boolean. That's its only primitive type. And then we can build things on top of it, everything else, and as a composite of that and build through that. So going back to the chess engine thing, a lot of the examples that Konrad uses is through the examples of, in chess. So the first one here, we see A1 is S1 by 3. So it's coordinates of the chessboard. So, and then you can see this goes down then to, we get the square of the board, the mappings of where pieces are and positions and current game states. So we're all built up from one single primitive type, which is super, super interesting. And then also we have a really, really interesting fact of this is what a hello world looks like in Planck-Kalkül. So again, a lot of gibberish here, but you can see here we have the hello world in semicolons going the whole way through. So in summary, Zuse was a pretty cool guy. When you imagine what he did, he developed the first known formal system of algorithm notation capable of handling branches and loops. Sorry, there's someone ringing my doorbell. I think I might have to go and get that in a second. So I'll try and blitz through this really quickly. But basically, another interesting fact is Zuse discovered that the calculus he had independently designed and used already existed and was known as propositional calculus, so a really advanced type of calculus, which he just discovered by himself. As part of his thesis, he wanted to develop his whole chess program, but that never actually got to happen for a couple of reasons. And I think leads to one of the most interesting quotes I found about him, which was that regards the chess program, in 1945, Zuse described Planck-Kalkül in an unpublished book. And the reason it was unpublished is that, again, going back to the time frame and being a very interesting time, the collapse of Nazi Germany, however, prevented him from submitting his manuscript. So if you think about any of the good reasons for not kind of finishing some like schoolwork or whatever, I think that's definitely a pretty good one. But yeah, that's Konrad Zuse, a very brief overview, filled probably with some doorbell rings and whatnot. But hope you enjoyed and thank you for listening. So
brilliant, thank you, Cian. I'm gonna stop watching that stream. Okay, so next up, I believe we have Amy, our own events officer.
Yep. Just 1 second. Alrighty, so kind of related to what Cian was talking about, I'm going to be talking about the first computer. And I'm Amy, by the way, so if anyone doesn't know me. So the first computer, a lot of people, when they think of like the first computer ever, they kind of think of something like this, huge kind of thing that takes up like entire room, and you have people pulling cables, moving them around and whatnot. That is like one of maybe the first that people would think of, but that's not actually the first computer ever that's known to us anyways. The first computer that's ever been discovered, it's an analog computer. It's called oh, okay, excuse me if I pronounce this wrong. Anaterita. I don't really know how to pronounce it, to be honest. I'm not going to even try. But it's a computer. It's an analog computer. It's from ancient Greece. And basically what it does is it predicts astronomical positions. So where the stars will be. It also predicts eclipses like decades before they're going to happen. So, back in ancient Greece, they're like, yeah, no, if I want to know about an eclipse, I'll just use my little mechanism, look it up. And it was also, well, they don't know exactly, but they think they might have also been used to track the 4-year cycle between the ancient Olympic Games, the 4-year cycle for that. So it did a couple of things. So where it was found is actually on the island of, oh, I don't know how to pronounce it. I'm really sorry, but it's Anacterita. Yeah, it's named after the island it was found near. It was found in a shipwreck off the coast of that island. As you can see, it's near Greece. So it was actually a Roman ship, which is interesting. So it was a Roman shipwreck, and they think that it was looted treasure, possibly but because the fact that it was on a Roman ship in a Greek area, they think it was looted treasure from one of the islands, possibly. And the shipwreck has been dated to about 70 to 60 BC, which they don't know if the actual mechanism is from that time period, but they say that it's probably like within a generation of that time frame, because they can only date the shipwreck itself. So within a generation of that, so like give it like 100-year maybe gap or something like that. And so when they found this shipwreck in 1901, and it was largely forgotten about until 1951, because people didn't really understand what it was. In 1951, people became a bit more interested in it, and then in 1971, what's it called? They were able to use X-rays to kind of scan it to see what it actually looks like. It has a bunch of gears in it. Sorry, I'll go. They're able to see that has a lot of gears. I think they roughly at the moment they have about 30 gears in the machine, and they only have, I think, the back end of it. So they don't actually have all of it. They only have about 1/3 of the machine. And so there's been a lot of like guesses and like people interested in trying to figure out what it does, how it works exactly, and what it would look like altogether. And so in 1951, yeah, like I said, people became interested in it again. Then 1957, there was also, they did the X-rays, and like slowly people built interest in it. And now, was it recently enough actually, they've been able to recreate it. So this is what they think it looks like. They have the dial, so they know that that's roughly what the dial looks like, but that's how they've been able to put it together for the first time in how they think it would work and how it would look overall. So as you can see, the face of it has like a lot of markings on it. They think it, because a lot of is not known about it, they think it's the days and months of this Soth calendar, which is an Egyptian calendar, which is interesting since it also has Greek lettering on it from the Greek letters describing the zodiac, so the 12 different zodiac. So, it's kind of a bit of a mismatch of two different things. So they think it's Greek, but it has Greek lettering, but it has like a possibly Egyptian calendar on it, which is, they're not really sure what's going on there. They think that it might also just be not even an Egyptian calendar. It could just be intervals of like 154 days instead of a calendar, but they're not really sure because obviously it's very old and you can't really see it that well. So it's a lot of about it is just a complete mystery because, again, it's very old, found bottom of the ocean. And the other problem as well is that because people lost interest in it in the 1901, like after it was discovered, people didn't understand it. It was just put into storage for a very long time. So another part of the problem is that we don't know how many fragments we have of it. So, for example, in 2005, they rediscovered one of the fragments in storage, and that obviously helped them try and figure out more, but they're not sure how many other fragments could be in storage or how much could be out at sea. In 2014 and 2015, they tried looking where the shipwreck was again, but they didn't really find anything that can conclusively be linked to it. They found a cogwheel that they thought might be part of it, but they're not 100% sure because, again, they don't have a lot of the stuff together, so they're not sure. So we might have more stuff that to complete it, but it's again just the whole thing's a mystery. But it is very interesting, and it obviously shows how advanced the Greeks were, or at least the people in that time period were, that they had something that crazy that they could predict, like eclipses and track the celestial, sky and everything through it and all that sort of stuff. And it was interesting is that, like, even though even though we don't like have everything all together, we can work out quite a lot about how it would maybe work. So yeah, but I think it's quite interesting. Anyway, what does this mean? So I think, crazy thought, it is so advanced for its time period, and that, like, clearly they were well ahead of their time, being able, because, for example, this kind of technology didn't come into Europe again because the technology was lost, and they're not sure why it was lost, but it came back in Europe at least in the 14th century. So that's a very long gap between those. So how could the Greeks possibly have something that advanced? Especially when they're just walking around in like their tunics and stuff. You mean, I don't know. I think, personally, aliens. Clearly, aliens came, gave them this technology, and we're like, yeah, we homies, we give you this technology to track all this cool stuff. And I think that obviously aliens are still here among us, trying to help us in their own ways, giving us technology, giving us the ability to track the stars and whatnot, and all that sort of stuff. So yeah, that's my talk about the first computer and probably the first alien visit, maybe, possibly, who knows. So yeah. Thank you for listening.
Thank you, Amy.
Okay, so this talks about UTF-8 and Unicode and why it is better as a successor to ASCII. So just jump right in. I'm going to talk about ASCII. So ASCII's been around from like the 60s. It stands for the American Standard Code for Information Interchange. And back in the day, this is what they used to have text appear. So if you think that for every character that exists, it's got like an assigned binary digit, ASCII did this with 7 bits, which you can tell this is old because it's not in sets of 8, which is what everything we do now is with bits and bytes. So with the 7-bit character encoding, they had lots of characters, but not enough. So they only had 128 possible characters, and they had enough for the alphabet in uppercase and lowercase, and a couple of things on your keyboard, and not really much else. So if you needed to use like accents for different languages or completely different languages that use other alphabets or characters, you just can't. So this is a pretty broken format for worldwide use. So like this, you can see that things would break if you try and send them across computers, and they did not support the same format. And this was definitely in a time where there was no standard. things like Windows and Linux weren't like just around. You had an IBM machine, or you had a Macintosh machine, or you had something, and these computers didn't really talk to each other. That wasn't how things worked back in that day. Nobody sent files to each other because it was kind of before the internet. At most, you might send a fax, and that was the best you got. And at that point, it's printed out in paper. You don't really need to encode it, so to say. But then the internet existed and ruined everything, or fixed everything eventually. So what was devised was something called UTF-8 in like 1992 or 93, and they could use anywhere from 1 to 4 bytes to describe a character, and this leaves for 1,112,064 possible characters, which is more than you'd ever need for anything. So with this, they could have anything from languages like Japanese, Chinese, Korean, Arabic, accents for vowels in European languages. Even I think it even supports like strange things like awsum, Old Irish, and things like that, just because they can. But there's one possible thing that might have gone wrong in that if you had old computers, it might not be backwards compatible. And you'll find that a lot of things in the computing world like have a lot of implementations to have things backwards compatible, because people do not like it when you bring in a new thing that breaks their old thing. That means they've got to change things, and change is bad, some say. So it was important that they had to make something that worked with the old stuff. So what they did was they made it so it just works. So if they can take an ASCII format with the 7 bits or 8 bits, and they'll just kind of like translate it in and make it work in 8-bit UTF format. And then also backwards, you can send a file that might have a lot of special characters for UTF-8 into an ASCII machine, and it might not work, so to say, if you were sending something written in Chinese. That would just come out as a garbled mess. But if you were sending something that had just ASCII characters like the alphabet, you would see all of the alphabet. So this leaves just enough backwards compatibility for things to work, for them to be readable. So, with that, UTF-8 and the Unicode standard came to be, and that's what we use for everything now. If you a lot of text editors will say in the bottom right the encoding format, and it probably says UTF-8 by default. So, but that's my talk. That's the history of character encoding. And thanks for listening.
Thank you for that talk, Ethan. I did not know a lot of that. So I'll be going next, and I'll be talking about working with legacy code. So, legacy code is defined as code not maintained by the original author, but honestly, that describes practically every system. In my experience, it's usually just a dinosaur system that's been around forever. So in this talk, I'll go through working with legacy code without murdering someone. Majority of you either work with legacy code, probably, or are students who will graduate and probably go immediately into working on legacy code. So this might be helpful. So first tip, resist the urge to throw it out the window. It may be absolutely terrible. It could be the worst code in the world. But if your company wants you to maintain it or clean it, you cannot restart it. If it is a production system and not permanently down, which it can't be or it would be redundant, then you need to fix and refactor it gradually and not rewrite it. So this little comic, it's mostly a fantasy in my opinion. You can't be a master at everything, and if you're a master at a legacy system, then you likely wrote or rewrote most of it, which kind of cancels it out being legacy. Okay. Documentation is your best friend. Unless it's a lie. and then it is evil. But wait. So you're on a legacy code base, and you're following these steps. You're trying to figure out what to do. The documentation's older than the code. It's wrong. The file won't open. Help? This was my actual thought process working on a legacy code system. The documentation was a LaTeX file that wouldn't compile. Tests. If they exist, run them, then run them again verbosely, then again. Understand the input and go through the tests to figure out what they do, what they're checking. There are none. No, wait, they're just hidden. Okay, half of them are skipped. And the other half fail. Okay. Coworkers. Talk to people, especially if they've worked on the system, but even if they haven't. No one has worked on this? Wait, no they have, they just won't admit it. And now they're hiding from me. Great. Logs, metrics, or errors. Logs are sometimes incredibly helpful, but if you're not sure what you're looking for, then they can be really overwhelming. Metrics are useful for finding overall problems, but likely you're already aware of them. Standard errors from the language or compiler are the same as working with the new system, but honestly can bury underlying issues. Bespoke errors are either the best thing ever or incredibly unhelpful. So the questions to ask are, does the company have logs or metrics? Does the system actually output them? And are there any errors popping up, and what kind are they? And then we have a little XKCD of, if you're seeing this code is in a state that I thought was an unreachable state. I could give you advice for what to do, but honestly, why should you trust me? I clearly screwed this up. I'm writing a message that should never appear, yet I know it probably will someday. On a deep level, I know I'm not up to this task. I'm so sorry. I am sad to say I've slightly come across errors like this, where when I found the person who wrote it, they went, that should have never happened. I put that in to try and catch this weird Heisen bug, which is a bug that that's very difficult to find, or doesn't happen very often. So, in summary, when working with legacy code, documentation is helpful but flawed. Tests are important if maintained. Coworkers can be incredible but also infuriating. Logs, metrics, and errors are essential but can lie and can be overwhelming. Moral of the story: good luck. I think that is me.
Let me start. Yeah, so I've given this talk before, but I think it deserves another go, because I thought this was one of the best talks I've ever given. It may be a bit incomprehensible and a bit too retro for some people, because I know there are so-called lightning haters out there that don't particularly like what I'm about to say, and don't think that this should be taught to people. I disagree, to be honest. I feel like this should be taught to everyone. It should be taught in schools to kids when they first go to school, if anything. But yes, as you can see, Lightning, humanity at its most retro, a charged talk about our first foray into electricity. So yeah, why Lightning? As I said, a bit of a valid question. As I see it, if we're gonna go retro, let's go real retro. And my proposal is that lightning was humanity's first source of electricity and power. And to explain this, I'm going to have to bring you through a little journey through human history with lightning, and how it's affected us throughout. Oh, there goes my camera. Throughout our entire history. And, I feel like it deserves this. So, our prehistoric history. Now, I'm going to come to the thing, naysayers and fire. I know straight up what some people have been thinking straight away is that, well, no, I think, fire was our first jump in like technology, and that, but I disagree. where did we get actual fire from? Now, I understand fire is important, but where did we actually get it from? In the first place, human ancestors, before we had tools, before we had the ability to make fire on ourselves, the only way we could get fire was through lightning strikes. And this is shown through with archaeological data that the only way we could get lightning, because we couldn't make it our fire, because we couldn't make it ourselves at this point, because we hadn't figured out how to do it ourselves yet, was through lightning. And there were specific jobs in the tribe that were people that were to look out for lightning strikes when it was like raining and thundery, and to then try and capture this fire and to nurse it throughout the entire days and weeks and for however long they could keep it alive. Now, lightning was the fire in the sky, as you can be seen here with this totally scientific representation of how lightning works. It enabled us to survive at night as humans, and also kept us warm. It kept predators at bay, and it brought us through much of what our prehistoric history was. It allowed us to cook things, allowed us to do all these things. And I know you're saying, oh, this is all fire, but the whole point of this thing is fire wasn't able to be brought to us until we had lightning in the first place. So I'll move on a bit past our real ancient history. So lightning hasn't just jump-started our technological advancements. It also molded our culture and our religious journeys as well. As humans began to settle down, societies and cultures began to form, and the growth of lightning had a major part, and lightning had a major part in many of these cultures and their religions and how they were shaped. Because many of these cultures saw lightning as a gift from the gods, which they should do, because lightning is amazing. So our ancient history with lightning, our best known example. Oh, did I skip that? No, I didn't. That's fine. The mighty Zeus. Now, a lot of ancient Greek history and religion was guided and decided by what the prophets of the pantheon of the gods said at any time. So if any states were going to go to war, they'd always, ask the gods, is this the right thing to do? Is this the best time to be doing this? Is this the best war we could be having at this moment in time? Which is understandable. Like, if you believe that the gods have ultimate control over anything, you don't want to ask them, like, is this the right thing to do? And at the centerpiece of this pantheon was the big boy at the top, the mighty Zeus. Now, Zeus got lightning as a gift from the Cyclops in the war against the Titans, and he used it to great effect to smite down anyone who dared to challenge him. Now, this made him the big dog at the top of Mount Olympus, and this religion, surrounded by the pantheon of gods, shaped much of ancient Greek life and culture. It enabled it to grow and to become one of the most. Jesus, I should have had a drink. Before this, my throat has got all dry. It enabled it to grow and to become one of the most influential nations in human history. They made huge advancements in science, philosophy, and the arts, and Zeus was nearly a huge part of all of those things. And the lightning he possessed played a huge part in how the people saw him and how they interacted with these parts of their own culture. This even continued on to the Romans, who, to be honest, they just kind of stole the Greek pantheon and edited slightly so that they wouldn't be caught for plagiarism. With the king of their pantheon being called Jupiter instead of Zeus. But essentially, many other nations were also shaped by lightning. For example, for one being Scandinavian mythology, and Thor was a great example. This has even made its way into our recent culture with the advent of the MCU and moving him from just being a god to being a god superhero. Now I know there's even more naysayers out there who would say, "Oh, he's just the god of thunder. He's not the god of lightning. Why would you say that?" Well, I say to you, do you know how thunder actually happens? Because thunder doesn't just, it's not just a sound that's made in the air. Thunder comes from the air being superheated at a quick rate, and that comes from the explosion that happens from lightning. So there's the only reason that thunder happens is because of lightning. And obviously, if you're going to pick something out when you're like, an ancient Scandinavian, and you see lightning, and then you hear this massive boom afterwards, the thing you're going to remember is the massive boom that like shook your thatched hut. Like, you're not going to remember though this flash of lightning beforehand. So that's why it ended up standing out. But the whole reason for thunder is lightning. Now, as I said, many other nations and religions were separate, were shaped by this, and it wasn't just European nations. It was also a big part of Native American culture, with the legendary Thunderbird. It was considered a supernatural being of immense power and strength, and was said to create thunder by flapping its wings and lightning by flashing its eyes. So it definitely wasn't just something that affected just human culture in Europe. It was a part of many cultures around the world. Now, I know I've talked quite a bit about ancient history and how it's affected lightning and everything like that. That's understandable, but I wanted to try and get that thing across. So, but I wanted to talk a bit more about our recent history with Benjamin Franklin as one of these people. Some of our brightest minds were fascinated by lightning in recent history, Benjamin Franklin being one of them. It led to some of the world's most powerful inventions and discoveries, such as the discovery that the electric charge, and also the development of the lightning rod, which this enabled us hugely. This helped us hugely because when back in that time you couldn't build buildings very tall, um, especially if you were building them out of wood, because these buildings, if they were tall enough, would attract lightning strikes, and would obviously, if they're made out of wood, go on fire. But now, if you have a lightning rod to be hit instead of the building itself, the lightning would harmlessly strike the rod, and the building would be perfectly fine. So this enabled us to build much larger buildings, and enabled us to actually grow as a society even further. And our fascination with lightning didn't just end in ancient history, as I said earlier. Thomas Edison and Nikola Tesla, they were both fighting over many different things based around energy, not actually literally fighting. Though, by I do love this gif. Um, they fought over whether the world should be, use DC or Marvel. No, sorry, not Marvel. AC power. But each of them also invented incredibly new technologies that were helped the world quite a lot, such as the Tesla coil. And I know it's not necessarily, there's a lot of controversy over whether or not Edison actually invented the light bulb, but he did end up coming, or he may have stolen it himself, but he was definitely the one that most people attribute it to. But it's not. There's a lot of controversy over that. But still, lightning did spark that debate over how could we harness it to make our own light. So coming to a charged conclusion. I know you want to hear more about lightning, but I can't go on forever. Lightning has shaped humans throughout all of our history, back when we were just hunter gatherers, all the way through our religions, up to more recent history, and into electricity itself, and even into as I just said, it enabled our survival as early humans, and it shaped our early religions and cultures. And what it has done is it's gone all the way into electricity now. That has become the little lightning in our pockets that run our phones, our computers. It runs the whole world at this point. And I think it should get more recognition than fire does, because fire is great and all, and it does help us quite a lot, but we wouldn't be here, we wouldn't have fire without lightning, and we wouldn't have a lot of our things that without lightning. So I hope you all enjoyed my talk, and here's a picture of Lightning Queen. Thank you.
Thank you, Nevin, for that illuminating talk.
You're welcome. I hope you all enjoyed it.
Do we have any questions on any of the talks? I know we've lost one of our speakers, but does anyone have any questions before we head off?
I'm happy to take any questions that anyone has.
Grace says, question, lightning isn't real.
That's not a question, that's a statement.
Good
It's
luck.
also a false statement.
It's
Good
also
luck
a
with the
false
Einstein
statement.
practical distro and any first years. Can we raid AWS? From Frost.
Can we raid AWS? I don't see why not, but I don't.
I mean,
what are they
sure.
doing at the moment?
I don't know how to do that.
It's real. It's not real. I would tell you lightning is very much real. I don't know why you're not fighting me over the more idea that fire was better off than lightning, but as opposed to the idea that lightning just doesn't exist.
I've never seen lightning, so I don't know if it's real. You know.
Okay. Yeah, that's fair.
All right.
Well, you get pictures, but you can Photoshop them. You know what I mean?
Mm-hmm.
Gotta play devil's advocate here.
I can't fight with Photoshop over that. Sorry. I guess Zeus was just using Photoshop to terrify some Greeks. So who knows?
Okay. I think we'll leave it there. I don't know how to raid. Let me see if I can try. Wait, no, because I don't want to show the
Zeus
Twitch
more
stream,
like more like sus. Redbrick is you is raiding AWS with 14 raiders. Yay!
Someone did it for me. Thank you.
Oh, hell yeah.